Okay, it's summer and right now it's very hot. But how high can the thermometer go? Is there an absolute limit to how hot temperatures can get, independent of Earth's climate or the conditions in this room? A point where it stops? A maximum heat that's impossible to exceed in the universe? To answer this question, which could very well melt the entire cosmos, we strangely have to dive in the opposite direction, toward absolute cold. But first, we need to discuss high speeds, the minuscule, and the true meaning of temperature. You'll see, it's a bit strange and fascinating because on a microscopic scale, temperature is movement. So we've been able to have fun calculating that. In air at 27 degrees, oxygen molecules move at an average speed of about 1,800 kilometers per hour. In other words, the molecules that make up the air around you are currently moving over short distances much faster than a commercial airplane. Obviously, it's impossible to know precisely the speed of each of the roughly 10 billion molecules found in a single cubic centimeter of air. They're constantly colliding and bumping into each other. And some of them certainly have speeds close to zero, while others can move much faster than average. And if no one has ever seen a storm magically break out in their living room, these molecules collectively lack a preferred orientation. They only keep their speed for very short distances until they meet other molecules, get disturbed, and change their respective trajectories. What you need to remember here is that the temperature of an object is actually nothing more than the measure of the average agitation of the atoms and molecules that make it up. And the greater this excitation, the faster their movement, and therefore the higher the temperature. In short, air at 30 degrees moves around much more at the microscopic level than air at 15 degrees. The air is more agitated than that trapped in a freezer. The idea is clear. Higher temperatures lead to increased agitation, with all the implied consequences. Since temperature is movement, as you keep cooling something down, the speed of the particles keeps slowing down more and more. We must eventually reach the point where they become completely motionless. No more heat energy left to give. This minimum temperature, below which it is no longer possible to go, since you can't move less than not moving at all, is called absolute zero. And nothing can ever be colder than that. In degrees Celsius, its value is minus 173.15 degrees or 0 Kelvin. If you take the temperature scale that sets 0 at its level, minus 173.15 degrees Celsius, that's super cold. But in a way, it's not that far from us. When you think about it, absolute zero is only about 300 degrees Celsius below the temperature of this room. So, of course, this ultimate cold isn't found in nature. The lowest temperature ever recorded on the surface of our planet was only measured at minus 89.2 degrees Celsius in Antarctica. In fact, even the coldest places we've been able to observe in space are measured at nearly 1 degree above that absolute. And actually, the closest we've ever managed to get to it is right now. In our laboratories on Earth, where small groups of atoms have been cooled to just a few 500 billionths of a degree. Above absolute zero, we're that close. And now, after having been interrupted by myself for quite a while, I'd like to return to the question I asked at the beginning. Is there, as the opposite of absolute zero, some kind of opposite to perfectly frozen matter? An overdose of movement, a maximum beyond which heating would no longer be possible? Or, to put it another way, how high can it go? And what happens when you're all the way at the top of the dizzying temperature scale? To find out, let's start this journey in search of the most frightening values that heat can reach. With the melting point of butter as our starting point. Add 1.5 degrees to that, and you've already surpassed the cruising temperature of the human body. Once you go past 42 degrees Celsius, fevers become deadly for our species. At 57 degrees, you reach the highest temperature ever recorded in the shade on Earth. At 100 degrees, water boils at normal pressure. At 120, you outlive extremophile bacteria in hydrothermal vents. Past 125, computer processors start to crash on their own for safety reasons. At 180, corn kernels turn into popcorn. At 327, lead starts to melt. At 357, mercury starts to boil. At 427, we reach the temperature measured on the surface of the planet that shares its name with the metal. At 462 degrees, Venus has the highest temperature ever recorded in our solar system. When we reach 525, something incredible begins to occur. We've just reached the Draper point, and now it's actually possible to literally see the heat. From this point on, You can tell that a metal plate is heated to several hundred degrees just by looking at it. Because almost all materials, whether liquid or solid, start to emit visible light through radiation, beyond 525 degrees. Below this temperature, all the matter was already emitting light, but in the infrared range, which is imperceptible to our eyes. And once past the Draper point, heated matter, whatever its nature, will continuously gain in brightness, becoming ever more luminous, transitioning from glowing red to white hot, then shifting to blue. At 962 degrees, Fahrenheit silver melts into a liquid. At 1200, we reach the temperature of the lava from effusive volcanoes, such as those in Hawaii or Réunion. At 1400, that's the maximum temperature of a candle. Once it reaches 1538 degrees Celsius, its ions turn to melt. Add about 1300 more degrees Celsius, and then it starts to boil. At this temperature, pure carbon is still solid. To melt it, you need to reach 3550 degrees Celsius. And wait until 4027 degrees to see it, in turn, start to boil. At 5660, we've gone past 5660. No element remains in a liquid state beyond that. That's roughly the temperature of the surface of the Sun, the photosphere, which is slightly cooler than the center of the Earth, estimated at around 6000 degrees. At 6600, we surpass the temperature of Polaris's surface. At 9500, that of Sirius, the sky's brightest star. At 24,000, Jupiter's estimated core temperature. At 37,000, that's the surface temperature of Eta Carina, a giant star about to explode into a supernova. And from there, to continue our ascent and find something even hotter than the core of planets or the surface of stars. We'll have to plunge into the depths of hell, where some of the hottest phenomena in the universe take place. Starting with the heart of our Sun, where there's a blazing furnace in which matter is heated to nearly 15 million degrees, which is both gigantic and relatively modest compared to the 200 million degrees reached at the center of red giants, which are engaged in helium fusion. And above all, to the nearly 2,500,000,000 degrees reached at the center of supergiant stars during the last days of their lives, before they explode as supernova, releasing into space in just a few hours as much energy as our Sun does over its entire lifetime. During the explosion of these giants, they form in place of the core of the vanished star, a tiny neutron star with an internal temperature of around 120 billion degrees. These stellar ashes of neutron stars are often considered to be the matter with the highest temperature that can be found in a massive and coherent object in the universe today. But it is possible to find, at least temporarily, something even hotter. Indeed, it has been possible to measure, at the level of quasars, supermassive black holes that sometimes contain billions of times the mass of our Sun. Matter accelerated and heated up to nearly 10 trillion degrees. A temperature so high that it exceeds that of Agdon, which, at 1,700 billion degrees, marks the limit beyond which you can forget about matter as you know it. Because as hot as it is, all the temperatures we've gone through before still kept atomic particles like neutrons or protons intact. But beyond 1,700,000,000,000 degrees, the energy involved becomes so high that protons and neutrons, hadronic matter, unable to withstand such levels of agitation, breaks down into smaller elements to take the form of a bubbling soup of plasma, quarks, and gluons. As such, the Hagedorn temperature can be considered the boiling point of the constituents of ordinary matter. You're likely curious about verifying this beyond working with equations on paper. Very good question. Thank you for asking me. In fact, we have been able to observe this matter during experiments conducted by humans on Earth. Because the Large Hadron Collider Particle Accelerator managed, by propelling atomic nuclei at high speed against each other, to heat matter up to 5,500,000,000,000 degrees. These temperatures are only maintained briefly and involve an extremely small number of particles. And to find matter that is even hotter, and in very, very large quantities, the only solution would be to go back in time, to the very first moments of the universe. It is believed, in fact, that in those distant times, more than 13.7 billion years ago, the temperature of the universe was momentarily 1,000 billion degrees. Before the expansion of space, its expansion cooled it down. But the craziest thing about all this is that theoretical physics tells us that this slightly intimidating temperature is almost certainly not the highest the universe has ever known. There was actually a moment in its history when it had a nightmarish temperature. which in turn draws a kind of impassable limit, the feverish opposite of absolute zero. This so-called Planck temperature has the staggering value of 141 septillion billion degrees. At this level, words become irrelevant. Even superlatives have vanished. It's so incredibly hot there that the sun's core seems like an ice cube in comparison. Writing about the excessiveness of this temperature without its intensity won't help you much either. How can you imagine something millions of billions of times hotter than the center of the sun? And yet, as striking as it is, this kind of upper limit doesn't come out of nowhere. Because the value of the Planck temperature comes directly from the fundamental constants of the universe that we know, it becomes apparent to us when we try, on paper, to concentrate more and more energy into a ridiculously small volume of space. There comes a point when it's no longer possible to keep increasing the agitation of the particles indefinitely, and that's when the realm of the strange and the disarray begins. The particle mass then begins approaching infinity. The wavelengths of the radiation become shorter than the smallest units of space. Monumental concentrations of energy are found in volumes so small that they cause the formation of Kugelbits, purely theoretical black holes formed from light and not matter. While even things as seemingly solid as space and time lose their consistency. And these are just a few examples of the countless oddities and problems that physicists face. At the Planck temperature, which is actually more of a theoretical limit than something physically insurmountable, this is the highest temperature that can be described, given our current knowledge. In other words, above that, the only thing you might see heating up are the physicists' neurons, caught up with laws that collapse and start to melt. So for now, we have absolutely no idea what happens beyond that. Because beyond this point, the extremely effective physical tools we have to describe the behavior of matter at very small and very large scales, which are quantum mechanics and general relativity, lose their footing. And until we maybe one day manage to find a unified theory, this temperature will remain the highest theoretically accessible in the universe. But maybe on the other side of that burning curtain, which for now obscures our view of the most distant times, there are even higher temperatures hiding. The coolest thing is that an innocent question like, can it get hot, sparked all this. How can it push theoretical physics to its very limits? And take you as far back as we can go in time, right up to the edge of the Big Bang? And as a result, end up wondering, damn, how could the universe have started? That's a question we'll have to set aside, because after getting seriously burned by the infernal conditions reigning in the primordial universe, I think it's time for us to return to the relative coolness of this room. To share with you an idea that I love above all else, namely that by stepping back to the beginning of the universe. At the time when those doomsday temperatures reigned, the fundamental particles that now make us up were already present in other forms in the earliest moments, momentarily plunged into that staggering furnace. And I think I'm going to let my neurons cool down with that idea.